All right, I think I'll at least start the preliminaries. So my name's Chris Davies. I'm an associate professor in theoretical geophysics. I live in the School of Earth and Environment, and I guess my interests are in the sort of dynamics and evolution of deep planetary interiors. So sort of the region that you can see in orange in this picture, the liquid cores of planets. And so that's really what I'm going to be talking about is how these regions generate planetary magnetic fields, why we care about planetary magnetic fields, and what they can tell us about the interiors of planetary bodies. So please do ask me questions at any point, ideally by using the microphone, only because I can't see the chat at the moment. So I might not see your question if it comes up in the chat, but please do interrupt me at any point. It's more fun if this is interactive. So, okay, so this is a sort of cartoon of the way planetary magnetic field, a cartoon of planetary magnetic fields in a sense. So, what we imagine is they're being generated deep inside a planetary body, and then the magnetic field lines, which is sort of being shown here in the blue, thread through the solid part of the planet, which is not generating the magnetic field, but they thread and they go on out into space. And so the entire planet, if it can sustain a global dipole dominated field like the one being shown here, this magnetic field will sort of envelop the entire planet and go out to many planetary radii. So I guess I thought I'd start by asking the question, why do we care about planetary magnetic fields? Because I realised that you all come from a variety of different backgrounds, and I'm going to offer you a couple of reasons. But the first is that it's generally accepted that large-scale magnetic fields play a key role in planetary habitability, and part of the reason for this is that they protect the planetary atmosphere and the surface environment from energetic particles that are incident upon the planet from the solar wind. So this cartoon is sort of showing the sun out here in white, and you can see this white sort of cloud of particles. Well, these are normally ionized particles that, upon interacting with the magnetic field, will sort of gyrate around the magnetic field lines, and they will actually enter the atmosphere normally near the poles, which is where we encounter the aurora borealis. Whereas if the magnetic field is not there, then these particles can directly impinge on the atmosphere, and they can start to react with the chemical compounds that are in the atmosphere. And ultimately, this is thought to lead to an erosion of the breathable components of the atmosphere. And this is really one of the arguments as to why Mars doesn't sustain a magnetic field anymore, because of the fact that the solar wind was able to impinge directly upon its atmosphere. And of course, once the magnetic field sort of allows an atmosphere to be established, this then sort of enables, through evolution, the preservation of surface water, and hence the emergence of sort of fundamental geological features such as plate tectonics, in which the surface of the planet actually becomes dynamic, and you can move, you can sort of recycle surface material into the interior. The other reason that planetary magnetic fields are important is perhaps rather more pertaining to Earth, and is a rather more sort of societal implication, which is that the magnetic field, through the shielding of the solar wind, the interaction between the field and the solar wind gives rise to a set of physical processes that are collectively known as space weather. And as you might imagine from the name, this is rather like conventional weather, only it's happening much further out from the planet in near Earth space. So things like coronal mass ejections, for example, so concentrated ejections of the solar plasma towards the Earth can interact with the magnetic field, and this can cause a variety of different effects. For example, it can cause damage to the electronics of low orbiting satellites. It can also cause disruptions to power grids, GPS, communications. In certain circumstances, it has even led to an entire blackout of a city's power grid. And you could imagine that if London's power grid was knocked out for 12 hours, that would be a significant event that our government would care about. And indeed, the government does care about space weather, because space weather is on the National Risk Register. So you can look it up and see that it is a known impact that the UK is sort of thinking about. And here's one of the examples. So what you're looking at here is the intensity of Earth's magnetic field. So darker colours are lower intensity, lighter colours are higher intensity, and it's higher intensity near the poles, and that is because the configuration is this dominant dipole. So this is like if you put a bar magnet at the centre of the Earth, then it's what's being shown in this cartoon, that the field lines will sort of encircle the Earth in this sort of akin to a bar magnet. There's this region of the magnetic field that is anomalously weak, meaning that it's weaker than what we would expect if the magnetic field was just a dipole. And the dots here that cluster in this weak field region are the at least of 2015, the reported electronic faults that occurred in aboard low orbiting satellites. And so when in the regions where the magnetic field is weak, the faults are more pervasive, and what will happen is that engineers will take normally evasive action. They will shut down electronics that are sensitive, sensitive electronic devices. Sometimes, if there is particularly high geomagnetic activity, then the entire satellite might, or much of the satellite electronic infrastructure might need to be powered down. But it's important to realise that this is a highly dynamic system. So this region of weak field is actually evolving over time. It's growing over time. And indeed, the global strength of the magnetic field is weakening. And so, there is quite a reason to understand how the magnetic field will vary into the future. And the final reason that we care about planetary magnetic fields is because they are something that we can observe about other planets. So we can use Earth-based observation, or we can use satellites, and we can measure the magnetic field of the other heavenly bodies. And this tells us something about the structure and the dynamics and the evolution of the interior of these bodies. And otherwise, we would have no hope really of understanding what's going on inside these planets. You might have seen in the news recently that the first, the first sort of 3-component seismometer was put on Mars, and this has led to a new determination of the size of its core. But of course, we can't put seismometers on the gas giants and on Mercury and Venus, and so really a magnetic field is one of our key probes of these bodies, along with their gravity signature. So this is the Earth's magnetic field. What you're looking at is the radial component, so it's a bit like the cartoon. The field lines go in the northern hemisphere, they come out in the southern hemisphere, and we've got this dominantly dipolar configuration whereby the field lines would sort of circle around as I'm showing with my cursor. Now, if this was a perfect dipole, then all of these contours would, in this projection, just be horizontal lines. But they're not perfectly horizontal, and you can see that there is structure in the Earth's magnetic field that means that it is not quite dipolar. It looks a bit like a dipole, but it's not quite. And this is at the surface of the planet. If we look at the Mercury's magnetic field on its surface, you sort of look at it and it's a bit like a lower resolution version of Earth's magnetic field. It's got the same polarity, and it's a bit like a dipole, but not a perfect dipole. The real difference comes when you look at the scale bar. Mercury's magnetic field is 2 orders of magnitude weaker than the Earth's magnetic field. And, one might ask the question, what on earth has caused that to be so? You look at Saturn's magnetic field. Saturn's magnetic field is remarkable because it displays almost no longitudinal variations. It's almost a perfect dipole, axial dipole magnetic field. It doesn't contain the structure that is seen in the other fields. So Venus. So I wondered if anyone could tell me anything that you know about the magnetic field of Venus. Would anyone like to offer up anything?
I think it's inverted, isn't it?
It's what, sorry?
It's inverted, it's the other way up.
Ah. Well, I'm sorry to disappoint you, but Venus does not have a magnetic field, and there has been, as far as we can tell, as far as we can observe, there's been no observations of a magnetic field on Venus in the past or at the present day. What about Mars? Does anyone know anything about Mars's magnetic field? Anything at all? You might have seen something about it in the news recently. Okay, well, it's not a trick question. Mars also does not have a magnetic field, but the key here is that it doesn't have a magnetic field at the present day. It used to have a magnetic field. We do have determinations of the intensity of Mars's magnetic field from meteorite samples around about 4 billion years ago. So Mars did have a magnetic field, but it lost it at some point, and this is the canonical explanation for why Mars's atmosphere was subsequently eroded by the solar wind. And then finally, Uranus. Does anyone know anything about Uranus's magnetic field? No? Well, Uranus's magnetic field is completely nuts. It's only been accessed by one satellite flyby, but it is just completely different to all the other magnetic fields. It doesn't have a dominant dipole configuration. In fact, its dipole is sort of pointing out of the page around about where my cursor is. And it's got all this funky structure. It's very, very strong. It's completely weird. And no one, an obvious question here is, why are these fields different? And what do they tell us about the interior workings of these planets? Okay, so I guess that's my sort of third science reason for why we might be interested in magnetic fields. And as you can gather, because I'm giving this talk, this has got something to do with fluid dynamics inside these planetary bodies. But before we move on to sort of the more fluid dynamical aspects of this problem, I thought I'd focus a little bit on Earth's magnetic field, because of course this is the magnetic field that we know the best. So previously, I showed you the magnetic field of the Earth at the Earth's surface. So this is the magnetic field that we would measure with our compasses. But we can also project the magnetic field down to the surface of the liquid core where it's being generated, and we can get a more high resolution view of the field. So what you're looking at here are two different plots of the magnetic field, and the difference is the time over which they've been averaged. So the one on this is the radial component of the field. Blue is field pointing into the Earth, red is field coming out. And the left one is an average over the 10 years, the decade between 2000 and 2010, and the right is a 400-year average over the historical period. So the left one's been measured using satellite observations. It's got very high resolution, and what you see is that the magnetic field structure is rather complicated. You've got this dipole, this dominant dipole, i.e. you've got more blue in the northern hemisphere and more red in the southern hemisphere. But really, when you look in detail, there's quite a lot of complicated structure. The dipole component is predominantly in these four lobes that you see really beautifully in the historical record. They're displaced away from the pole, so the field is actually not is strongest away from the pole, showing you that it's not a perfect bar magnet. And these patches are sort of almost symmetrically displaced with respect to the equator. And we'll come on to sort of why that might be a little bit later. You also see all these structures around the equator, a bunch of patches here. And if I were to show you a movie, you would see these patches that form a sort of wave train that move from east to west. So you get quite a sort of complicated field configuration. And there tends to be less going on in the Pacific region than there is in the Atlantic region. There's a lot more variability and a lot more structure in the Atlantic than the Pacific. We then, unfortunately, as we go back in time, our observations degrade, and we have what, I said this one was made from satellites. The one in the top right was partly made from using ships' logs about when ships sailed the seas, they would take regular compass measurements to find to find out their location, and you can use that to reconstruct maps of the magnetic field. As you go back in time, you have to use less direct measures. So, for example, the map in the bottom left, one of the ways it was constructed was to use the fact that when ancient civilizations fired pottery in a kiln, the pottery cooled in the presence of Earth's magnetic field, and that the pottery would then retain a remnant magnetization that could be dated. The strength of that magnetization could be obtained, and if you got enough of these samples, you could produce a bit of a map. And what you see as you go back in time is that the field has moved around a bit. No longer have you got these nice displaced patches. You've still got some structure near the poles, but certainly stuff in the northern hemisphere has moved around a bit. And as you get into the longer time period, so this is now 10,000 years on the right, you've almost got the emergence of a third patch on the in the southern hemisphere. So the point is that the field is dynamic, and you can really see that when you look over longer time scales. So as our data degrades, we only have, and we can't build these sort of nice pretty pictures of the magnetic field. Once we go back more than about 10,000 years, all we can access is the strength of the dipole component of the field. And that's what's called the dipole moment here. And it's being plotted over the last 2 million years. And these red points here, the red vertical lines where the field strength goes very low, is where the polarity of the field reverses. So this is where the predominantly the north, the blue and the red will swap, and the red will go into the northern hemisphere and the blue will be in the southern hemisphere, i.e. the field is pointing in the opposite direction. And what this plot shows you is that the field reverses a few times every million years, but it does it sporadically, and no one knows, no one is able to predict when it will reverse, despite what you might see sometimes in the media, and no one knows the mechanism that causes these reversals. It's completely unlike the sun, in which the sort of reversal is periodic. Here it is completely aperiodic. And if we look over longer time series, this is now, the top panel is 2 million years, the bottom panel is now 150 million years. Each black and white in this barcode is indicating a normal or reversed polarity. So each transition from black to white represents a reversal. And you can see that the frequency content of this record is extremely complicated. We have regions here known as supercrons, where the magnetic field did not reverse for tens of millions of years. And then we have, right next to that, regions, periods of time like the Jurassic, the hyper-reversing Jurassic, where the field was reversing all the time. So our model of the magnetic field of the Earth, and probably of other planets, has to be able to explain this sort of chaotic, non-deterministic temporal variability in both the field strength and its direction. And the other thing that I just want to point out about the field, you know, and this is really telling you hopefully why this is a sort of enriching field of study, because it's a very complicated sort of dynamical system. The other complication is that the field is incredibly old. So as we go back further and further in time, what I'm now plotting is the field strength on the vertical against age in millions of years, but 4,000 here is 4 billion years ago. So we're now getting back towards the formation of the planet, and you can see the Earth's magnetic field, which is just all these dots. The colours are just binning the data in various different ways, but the field has been around for billions of years, up to perhaps 3.5, 4 billion years, and there's no real evidence from the record that it was ever turned off. So whatever process has been generating the field has been doing so for the last 3.5 to 4 billion years. And it's been producing this highly dynamic field where the field reverses and changes its strength and direction in unpredictable ways. So the theory and any of our attempts to understand the physics behind this process has to be able to capture this incredible range of variability that we see in our observations. Does anyone have any questions at this point, before I sort of move on to more the sort of physics and how we describe the way the magnetic field works.
Yeah, I've just got a question. How did you get data from 150 million years ago for the reversal of polarity? So the barcode chart.
Yeah. So here, this is from the spreading of the seafloor. So what happens is that a mid-ocean ridge, you've got upwelling of hot material. The material cools when it reaches the base of the ocean, and there it cools in the presence of the magnetic field, and the direction of the field that is preserved on the ocean floor is the direction that it was pointing, and so that's how you can see the differences in direction. Does that make sense?
Yeah, sort of.
It's because it's as the sort of sediment at the base of the ocean cools, it locks in the direction of the magnetic field. So that is the magnetic moments of the minerals comprising the material all line up and point in the direction of the Earth's magnetic field, essentially.
Okay. So, yeah. Thank you.
No problem. Any other questions?
Yeah, I've got one as well.
Go for it.
I was wondering, do you know what causes the shift in the poles? Or is it just something that we don't understand yet?
Ask me again at the end, because I mean, ultimately, we don't have a good idea at the moment, but I can give you a more well-rounded answer when we've discussed some of the physics of the process.
Okay.
Any more questions?
Yes, I have a question. Earth has a 23.5 degree tilt in axis. Does it has an effect on the magnetic field? That's why it is irregular, because of the axis tilt.
Oh, but because of the tilt of the geographic axis.
Yeah.
It doesn't have a significant effect. I mean, people have argued that actually you might know that the axis precesses over time. So the Earth's axis moves in time in various different ways. Yeah. And people have argued that sort of rocking of the core, essentially you can just imagine that the solid mantle, which contains a fluid inside it, is rocking the fluid around, and that is people have argued that is able to generate a magnetic field, and that's not the main mechanism we think about on Earth, but it certainly could have been the main mechanism on something like the Moon.
Okay, thanks.
Okay, thanks for all your questions, and please do just shout them out as and when. So I guess I thought, right, okay, let's think. So what have I basically said in a nutshell? I've told you that Earth's magnetic field, which is sort of our canonical example, the magnetic field we know the best. Earth's magnetic field, it's strong, it's of large scale, it's this large dipole that envelops the entire Earth. It's long-lived, billions of years old. It reverses irregularly, and to explain all of this, all of those observations, it must be of internal origin. Fields external to the Earth vary on much more rapid timescales of seconds, milliseconds. We have to look inside the Earth to find out where the field is generated. And I've sort of already given you the answer as to where the field is generated, but there is still a slight wrinkle that we have to think about. So this is the basic four-layer structure of the Earth. The very thin yellow thing up here is the crust. So this is solid silicate. It's got a bunch of radiogenic material in it. The silicate mantle is in green. The core, the liquid portion of the core, is in light red. The solid portion of the core is in dark red. And so if we're looking for where to generate the Earth's magnetic field, then we quickly come up against a problem. What I'm showing here is the depth inside the Earth. So the center of the Earth is at the bottom of this plot, and that would be in the center of the right-hand plot. The surface of the Earth is at 0. And you're looking at temperature in degrees Celsius along the horizontal. Now, the Curie point above which materials lose their permanent magnetization is only a few hundred degrees Celsius. So you can see that you don't have to go very far inside the Earth before you were at very, very high temperatures, you know, over 1,000 degrees Celsius. So there is no hope that permanent magnetization is stored within the Earth, right? And as we get down to the bottom of to the Earth's core, the top of the Earth's core is at 4,000 Kelvin, you know, and the base of the core, where the inner core becomes solid, is the temperature of the surface of the sun. We're at extreme temperatures here. So it's clear that a silicate is not going to generate a magnetic field because it has a low electrical conductivity. And I'll show you later why the electrical conductivity is so important. But clearly, you know, we just think about our basic knowledge of magnetic fields, even from A-level physics, if you did it, you know, and we expect metals to carry magnetism. And we know that the Earth is differentiated into a lighter silicate portion, and then all the iron is in the middle because the iron was heavy when the Earth formed and it dropped to the center. So because we can't have permanent magnetism, we have to be looking for the metal to be able to generate the magnetic field. Okay, and the fact that we can't have permanent magnetism tells you that it must be the liquid iron outer core that is generating the field, because if you can't have permanent magnetism, the only way you can generate the magnetic field is by changes in electric currents. Okay, so the idea is that the magnetic field is being generated in the liquid portion of the core, because here you can get fluid motion generating electric currents. The electric currents correspondingly generate magnetic fields. So this is sort of where our fluid dynamics comes in, because we need to understand how this liquid portion of the core is working. And the canonical view is that what is happening is a dynamo process. So broadly speaking, what a dynamo process is a process that converts kinetic energy of a moving fluid into magnetic energy. Now, of course, that's a little bit vague, and I'm going to talk in a lot more detail about the way that process works, but that's the basic idea. So we've got a fluid here. The fluid motion is sort of being shown in this cartoon by yellow helical lines, and this sort of arises from Earth's rotation. The magnetic field lines that are shown in black are sort of getting stretched and twisted around in some complicated way. And the process by which the fluid is set in motion is convection. Essentially, what's happening is that the solid portion of the Earth is extracting heat from the core. This is making the top of the core anomalously cold, setting up buoyancy forces that is driving convection. And as you hopefully all know, convection arises when you have sort of thermal or compositional anomalies across your fluid. So really, this is where the fluid dynamical problem comes in, understanding this so-called hydromagnetic dynamo and how the process of conversion of kinetic energy into magnetic energy is achieved. And this dynamo process is what we think is happening in all of the bodies that generate global magnetic fields. So in all the bodies I showed you before, in Earth, we think it happened a long time ago. In Mars, it happens in the gas giants, in Jupiter and Saturn. It's probably happening somewhere. It could be in Uranus and Neptune, perhaps in subsurface oceans, but nevertheless, it's this basic process that is happening. There's reason it happens in moons. You know, it happens currently in Ganymede. It probably happens somewhere in exoplanets, if only we could observe them to a sufficient level of accuracy. So there's not many equations in this talk, but I sort of felt it would be remiss of me if I didn't at least give a sketch of what's going on here. So there's not a huge amount of equations. Any of you who have done an electromagnetism course will have seen Maxwell's equations. Okay, these are the equations of electrodynamics, and in the non-relativistic limits, they can be written like this. So the top one says B is the magnetic field, and this one says that there are no poles of the magnetic field. Unlike electric charges, there is no corresponding magnetic charge. Ampere's law says that circulating magnetic fields are generated by electric currents, J. Faraday's law says that time-varying magnetic fields are generated by circulating electric fields. Ohm's law is an empirical relation between the electric current density, the electric field, and this thing U cross B, which is the current that's being generated by the fact that the electrical conductor is moving at a velocity U. And Gauss's law, in this particular limit, reduces to the divergence of the electric field being 0. But what's nice about these equations is, aside from their sort of elegance and general beauty, is the fact that we can construct a single equation that describes the generation of the magnetic field. And I just like to sketch for you how that's done, because I thought it's perhaps something you haven't seen before. So we start off with Faraday's law, which, for the simple reason that it's got a dB by d time in. And we can pop in the E, we can use Ohm's law to eliminate the electric field E. And when we do that, we get the top equation here. Okay, so we've already sort of almost succeeded in what we want to do. We've got the rate of change of the magnetic field. We've got one term here, curl of U cross B. It's got the magnetic field in, and we just need to get rid of the J. So the J we can sub in using Ohm's law, which we get here. And you get this quantity 1 over mu naught sigma, sigma being the electrical conductivity, mu naught being the permeability of free space. And this quantity is conventionally written eta, and it's a diffusivity. It has units of meters squared per second. It's like a thermal diffusivity or a viscosity, a kinematic viscosity. Has exactly the same units, plays the same role, broadly speaking, in the equations. So if we take the diffusivity to be constant, then we can write a single equation that describes the evolution of the magnetic field. This equation is called the induction equation. It plays an utterly central role in our understanding of how magnetic fields are generated in the sun and stars. In the planets, it is a crucial equation, but it is of no greater importance than the momentum equation that I'll discuss in a bit. So we've got a sort of complicated term here that involves the fluid velocity U and the magnetic field, and then we've got a sort of standard diffusion term on the right hand side. And there's a sort of nice way of extracting some information from this equation without going through a huge amount of effort, without doing a whole very complicated solution process. And I thought I would again just sort of sketch that for you so that we can generate 3 fundamental results that arise from the induction equation. Okay, so if we take the induction equation in its previous form, you can use, as you do a lot in fluid dynamics, you use vector identities. We use the fact that the magnetic field is divergence free. If the flow is incompressible, hopefully you've seen the incompressibility condition before, that the divergence of U is 0. And you can then write the induction equation in this very convenient form where the big D's are now the material derivative. So this is the rate of change following the motion of the fluid. Okay. And then to proceed, we do something that, again, hopefully you've seen before, which is dimensional analysis. We try and write this equation in terms of dimensionless numbers. So we can say that all the stars here are dimensionless quantities, and all the scalar quantities here, like this big V, are dimensional. So V is just a characteristic flow speed. The time scale here is what's called the advective time scale. It's the time scale for a fluid parcel to be advected through a length L at the velocity V. And then scalar B is just a strength of a characteristic strength of the magnetic field. And when you pop these this set of relations into the induction equation, you get a set of dimensionless terms, and you get a single dimensionless number that pops out, this thing called Rm, which is the magnetic Reynolds number. It's exactly like the Reynolds number that you know and surely love, except that it's got this magnetic diffusivity eta in rather than the viscosity, the kinematic viscosity. In the Earth, this number is about 1,000. Which tells you that the second term, del squared B, is strongly subdominant to the other terms in the Earth's core. In the Sun, this Rm might be 10 to the 8, absolutely enormous. Okay, but we get a nice equation from which we can extract some simple physical intuition. Okay, so here's the equation. The first thing that you notice about this is if you set the velocity u equal to 0, you end up with a diffusion equation. And that tells you that in the if u is 0, the field will decay by diffusion. Any field that you put in, it will decay away in a diffusion time. So you've got to have some u. The velocity is crucial to generating the magnetic field. But you can say more than that, because the only way that the magnetic field grows on the left-hand side is through this source term, b dot grad u. And what's coming in here is not just the flow itself, but the gradients of the flow. So if you've got a uniform flow, that's no good for you. You need a flow with gradients in. Okay, so that's the second thing that you can learn from this equation. Not any flow will do. You need a specific type of flow, one that's got some gradients in. And it turns out that convection is great for this, because if you ever seen convection, you can generate some pretty complicated flows through convection. And when the convection becomes turbulent, you can generate some pretty complicated U's. And then finally, we've got this factor 1 over Rm. Okay, and as Rm goes up, the diffusion term becomes smaller, except when it can adopt very, very small length scales. You can still make this term on the right-hand side comparable to the other two if the length scale of the field is small enough. And that's sort of what's being shown here. So Andrew Clark, who was a CDT student a couple of years ago, did a lot of work on how you can efficiently solve this induction equation. And this is a particular example from one of his papers where he imposed this particular flow called the Roberts flow. So here the flow is just being imposed so you can solve this equation on its own. And these are two examples of a component of the magnetic field when Rm is pretty low and when it's pretty high. And you can see that when Rm becomes really high, you get very complicated structures where the magnetic field is weak, except in these very narrow regions where that allows this diffusion term to be comparable to the scale of the other terms. Okay, so that's just a sort of quick run through of the importance of the induction equation. So would anyone like to ask any questions about the induction equation before I sort of move on to consider how we generate this velocity? Okay, well, we can talk about it at the end if we have time. But the real key, here Andrew has just imposed a flow, hand of God, put it in, and out comes the solution. But of course, the flow is itself a solution of the Navier-Stokes equation. Okay, and so that's what I really wanted to talk about next. So I'm sure you've all seen the Navier-Stokes equation. I'm not going to talk about the Navier-Stokes equation in a huge amount of detail. What I wanted to do is point out some facets of the Navier-Stokes equation that that are particularly interesting in the geophysical context. Okay, so all your variables are down in the right-hand side, and there's probably, hopefully here, a few terms that you already recognise. So the Navier-Stokes equation is just really a statement of Newton's second law of motion, only applied to a moving parcel of fluid. And so the acceleration terms are all on the left-hand side. And the first two are the material derivative, where you're following the motion of the parcel. And then you've got the sum of all the applied forces. And you will have certainly seen the pressure gradient force and the viscous force, which is on the right-hand side, where because we're in a very simple rheology, it reduces to this particular form. The alpha term, this one is the buoyancy force. This is the convective driving. T is the temperature anomalies that are driving the convection. But there are two terms with which you're perhaps a little bit less familiar, and these two terms turn out to be really important in the dynamo process. So the first is the Coriolis effect, Z cross U. And the classic example of where you see this is in cyclones in the Earth's atmosphere. So you've got a low pressure centre at the centre of this cyclone, and the observation or the question is, why doesn't all the flow just flow towards the low pressure centre? Why does it end up spiralling around the low pressure centre? And the answer is that because we're in the rotating frame, the Coriolis effect is deflecting the fluid around. So the way you do this is you take this picture here, and where my cursor is, you use the right hand rule. You put your thumb so that it's coming out of the page. Your index finger is then following the flow in along the black lines, and the resulting force, the Coriolis effect, is pointing in the opposite direction to where your middle finger is pointing, and that means that it's pointing along the red. So essentially the Coriolis effect is always pushing against the pressure gradient, trying to, and so the flow is trying to go in, but it ends up circling around, right? So when you're in these sort of rotating frames, you tend to get vortex structures like this, and you'll see some examples later. The other effect that is crucial is the magnetic force, the Lorentz force. And the simple picture of this is you take a bar magnet, and the magnetic field is pointing from the red to the green. And what you do is you move your piece of electrically conducting material in to the bar magnet. This generates an electric current that's pointing in the blue direction, and the resultant force, the Lorentz force, is to oppose the motion. So as you push in your electrically conducting material, you'll feel a resistance, and that force is here, curl B cross B, the Lorentz force. And it turns out that these forces are really important for what goes on in planetary cores. So first of all, because they're both very complicated, what we'll do is we'll cross out the Lorentz force and have a look at what happens then. And if we do that, again, we write this in a non-dimensional form. It's really helpful to write things in dimensionless forms because we have fewer variables, and the parameters that we do have left tend to be ratios of important effects. So you might well have seen the Rayleigh number before if you've ever looked at convection. It's basically telling you it's the ratio of all the effects that are driving convection, in this case the buoyancy, divided by all the effects that are resisting convection. And these are normally diffusion, that would try and wipe out any thermal anomalies in the system. The Prandtl number is the ratio of the viscous diffusion and the thermal diffusion. And here the key parameter is the Ekman number. It's the ratio of this term, the viscous term, divided by the Coriolis effect. And it tends to be really small in planetary cores. And this produces a very significant problem, which is shown here. So the conditions we want to be at are down here, shown by the Earth. And quite frankly, I could substitute in a number of other planets as well, and you wouldn't be too far away. The Ekman number is always incredibly small inside a planetary body, in a planetary core. And what's being shown here on the vertical is the Reynolds number. So that's essentially just a measure of the fluid velocity, or it's the ratio of the inertial terms and the viscous term. And the Reynolds number is always high in a planetary core, essentially because the viscosity is always very low. So you have this very complicated limit to take where you need turbulent flow. Your Reynolds number is far above the laminar to turbulent transition, but you're very rapidly rotating. And this causes all sorts of problems for numerics and for experiments, because it involves representing a huge range of spatial scales and integrating over relatively long time periods to get to steady solutions. So currently, most of our work has been done over here. And if you can just appreciate from the numbers on the graph that this is a huge distance away from the planet. So, this is going to be an enduring topic that is going to live long, because people are going to have to think very cleverly about how to try and bridge these gaps, because just waiting for larger computers won't do it. But what has tended to be done is that this means that we can't just stick the Earth into our computer and press go. So we really need to understand the fluid dynamics of how these systems behave, so that we can see when the behavior of the system changes. And that's what I wanted to show you here. And again, this is the work of another CDT student, Rob Long. We've now started to make decent progress in this area, and Rob really sort of elucidated some of the basic transitions that happen in rotating convection. Produced a nice paper in the Journal of Fluid Mechanics. So when your convection is not very vigorous, otherwise saying when the Rayleigh number is relatively low, the viscous force can still be important, the rotation is almost always important, and you get a regime that looks like tall, thin columns. So you get a bunch of small scale flow structures. They're small scale because the viscosity forces the flow to exist on small scales, but everything is aligned like this. So you can see the vortex structures that arise from the rotation. The other thing the rotation does is make all these columns long and thin. So each one of these vortices is like a column extending up and down. Okay? So you get these coherent columns, and this is where the viscosity is important. As you push up the Rayleigh number, you start breaking this rotational constraint. You can see now you haven't got nice coherent columns. There's still what is called anisotropy, right? The length scale in the vertical direction is a lot longer than in the horizontal direction. But you've now got sort of turbulent motion, and the inertial effect is becoming important. It's essentially replaced the viscosity and the force balance. And this is where you've got rapidly rotating turbulent convection. We then get to this regime that quite frankly is just nuts. It's called the transitional regime. And this is where there is a gradual loss of the rotational constraint. And one of the things that is remarkable about it, if you're sort of interested in more theoretical aspects, is there is no scaling behavior for this regime. Even when you plot things in a log-log space, everything is curved. And this is generally a bit of a disaster for most of your theories. But eventually, if you keep pushing up the Rayleigh number, driving the system harder and harder, you get to a point where the system is almost behaving as though it's not rotating. Okay, so now finally the Coriolis effect is no longer particularly important, and you get something that looks more like three-dimensional isotropic turbulence, which is shown again over here. And so what you can do is you can actually, at least for the case where there's no magnetic field, you can put all of this together and get a diagram, right, that shows as a function of your two main input parameters, the Ekman number and the driving force, the Rayleigh number, where you get these transitions. And you can find regions in parameter space where you access this rapidly rotating regime and regions where you don't. And we think that really this rapidly rotating regime is the one that's relevant to planets. But of course, the real planets live a long way up to the left of this plot. And so that there is still quite a lot more work to do to establish whether this rapidly rotating regime really carries on up here. But what's nice is that at least you can actually break it down, break the problem down, and see where the behavior changes. Now, when you add in a magnetic field, you can't do that because the simulations are harder to run. They take longer to run. You haven't got that much information. So what I thought I'd do is just show you a simple comparison. So this is a nice paper by Nathaniel Schaefer and co-workers, where the top half of each of these plots is a simulation with no magnetic field, and in the bottom half is the same simulation, the same conditions, only there's now a magnetic field being generated by a dynamo process. C is like the temperature, it's the anomaly driving convection. UR is the radial velocity, so that's pointing out and in. U phi is the azimuthal velocity, so that's going around in longitude. And then the bottom left panel is just the magnetic field. And what you can see, just in a qualitative sense, is that the magnetic field matters. This is the role of the Lorentz force. It's changed the structure of the flow, right? So whereas here we had all these smaller scales, we had a lot more sort of small scale features. Now things tend to appear in these sort of larger scale ribbons of sort of intense flow with not much going on everywhere else. The azimuthal flow is completely changed. In the non-magnetic case, you have these winds. These are large-scale winds that are going sort of around the domain. They're all broken up and they're completely gone in the case of the magnetic field. So this is just an example of how the magnetic field, though it's being generated by the fluid motion, acts back and changes the fluid motion. So there is like a harmony that is being set up between the field and the flow. We also know that as you drive the system harder, what happens is that when you're driving the system relatively weakly, you tend to get these nice dipolar field structures. Okay, so it's dipolar because you've got predominantly green in one hemisphere, predominantly purple in another, and all the flow is this columnar flow aligned with the rotation axis. But as you push the Rayleigh number higher and higher, so as you go into this more rapidly rotating turbulent, you can get rid of the dominant dipole. You lose the dipole, and all you've got is a small scale field being generated by small scale flow. And there are starting to be theories that put this together. Essentially, this is a nice paper by Aruba and Dormy. What you're plotting here is the dipole dominance on the vertical against some sort of transition parameter. But what this is saying in physical terms is that the dipole field is lost when the inertia becomes important. So up here, inertia is weak, it's weak, it's weak. Suddenly it's comparable to the other forces, and it disrupts the columnar nature of the convection, kills the dipole. So I just thought very briefly at the end, I'd return to my main question, right? There's a huge amount of fluid dynamics that can be done here, even when you don't consider the magnetic field. There's a huge amount that's going on. But I thought I'd just like to return to, why are these fields different? We have these observations, and what does this tell us about planetary bodies? Well, I didn't mean that to happen. I've obviously got to go through all these transitions again. Can you just show me that? Yes. So, I mean, ultimately, we don't know. We don't have a definitive answer to this question. The differences in force balance is probably part of it. Uranus might well be in this regime where the rotational effects are weak and the buoyancy driving is strong, and this produces the complex non-dipolar field. But there are lots of, so these force balances are certainly important. It's integral to understanding these fields. But also, there will be other factors at play. In some of these bodies, probably not all of the core is actually convecting. Some regions are stable to convection, in which case these regions are called stratified. They're not undergoing convection. There will also be complicated material properties. In the Earth, we tend to take things like the electrical conductivity as a constant, but in a gas giant like Saturn, the electrical conductivity can vary over many orders of magnitude. And there'll also be interactions between the core and the solid container to which the core is confined to. And so there's still an awful lot of work to be done in this area. But ultimately, what I've tried to show you is that these magnetic fields are telling us something about the deep interiors of these bodies. They're telling us about not just the core, but the balance of forces, the processes that are going on in regions that we would otherwise have no hope of observing. So with that, I thank you for listening, and I'll take any questions.